Hello, I'm Ed Pegg Jr., and welcome to another episode of Mathematical Games. Today we'll be talking about fractals, and this is the image I've always been using for this series, and it includes fractals as it happens. A Nautilus fractal using uh, the super golden triangle and also the psi-quad substitution fractal as a background. So I do quite a bit with fractals. Mathematical Games is a series based on the works of Martin Gardner, who did a series for Scientific American for 25 years, and they were collected into 15 books, and they were very influential for many mathematicians, including myself. And I'll mention that we have many fractal items at both demonstrations.com and also at the Wolfram function repository and at MathWorld. So there's quite a few fractals mentioned in Gardner's works, including Penrose tiles, surreal numbers. Uh, Fractal music is one of the titles of one of the books. The dragon curve, reptiles, here's where he talks about Mandelbrot's fractals, including some space-filling curves such as the piano curve and the Sierpinski curve. And over here is a small flow snake by Bill Gosper, who's been a longtime friend of mine. And Benoit Mandelbrot was also a friend of mine. When I first corresponded with him, I basically asked him for permission to use the Mandelbrot set, and he replied that I was the first person to ask him for permission. But since it was a mathematical object, he didn't need to give permission, but he gave me permission anyways. So I might be the only person with permission from Benoit Mandelbrot to actually use the Mandelbrot set. Later, we run a site called periodictable.com, which includes many items, examples of elements. It's run by Tale Gray, and I helped them build the periodic table, which won an Ig Nobel Prize, not the Nobel Prize, but the Ig Nobel Prize, which is kind of the joke version of the Nobel Prize. We won it for building the periodic table. And Benoit Mandelbrot liked this thing. And when he was going to give a talk at the United Nations, he asked to borrow our uranium sample. He took it to the United Nations on the subway. And during this talk, he pulled out our uranium sample and put it on the podium and just sort of mentioned that no one checked that he was carrying uranium. And he said this might be a problem with nuclear security, that he was able to go through New York City on the subway with a large chunk of uranium, and it didn't cause any trouble for him. And then he sent it back to us. So you can get fractals in many different ways. And one way of starting right off is just to look at binary numbers. You get a fractal pattern out of the binary numbers. Here they are arranged with the zeros and ones arranged vertically. And you can continue the pattern on. Ternary also leads to a fractal. All bases lead to fractals. So just numbers themselves have a fractal quality to them. His own famous start with fractals began with How Long is the Coast of Britain in 1967. So here's the coast of Britain. And as we refine it, we get a more and more accurate measurement for the length of the boundary. And if you keep on getting more and more detailed, the fractal boundary of the coast of Britain becomes larger and larger. So he basically concluded that it was meaningless to talk about the length of a coastline since it could be so varied. Another thing he looked at was the Julia set. And there are some places where it's connected and some places where it's disconnected. The Julia set basically repeats this operation over and over again. And that's sort of a feature of fractals, is to take something and do it over and over again. Here's another Julia set. And this is one of our demonstrations. You can basically play around with different measurements. And of course, there's many other items online for playing with Julia sets and other items like it. So here's a disconnected Julia set. So one thing Mandelbrot wondered is, where is the Mandelbrot set connected? And so he finally did a printout, and he got this really strange object over here, which is now called the Mandelbrot set. So you can actually generate the Mandelbrot set by using this function and iterating it over and over. And it's also possible to zoom in on portions of the Mandelbrot set, and that will bring you various zooms at various levels. And there are one thing that's worth looking for online is Mandelbrot zooms. There's many fascinating ones where they'll spend a few computer years or so zooming in on one particular section of the Mandelbrot set, and I find those very fascinating. Another type of fractal often seen in advertising is the Drost effect, and this is the original Drost, where they have a image, and this is a interaction version where you can vary the size and the magnification. But basically, this concept of infinite regress to an object within an object over and over again is another type of fractal, another type of recursion. So here's a maze I came up with where basically you have this maze and there's an infinite number of copies of the maze within itself. And the object is to get from 1 to 8. And if you have enough copies of it, it's not too difficult to follow the maze in and out to get through it. But if you only have a single copy of it, it's quite difficult. There's much more complicated fractal mazes in a maze program. If you just search for fractal maze, you'll get into a whole bunch of nearly unsolvable mazes, which are quite tricky. One basic fractal mentioned by Gardner is the piano curve. And there's different piano curves. You can basically start with a simple one, and they can get more and more complicated as you change the rules. So these are all different space-filling curves of various sorts. A classic one is to build biological objects, such as trees, just recursing on the branching over and over. You can also do the same thing with triangles of various sorts. A turtle graphics, where you have a particular rule and you iterate the rule, can give all sorts of different fractal curves, such as these. Here's a demonstration that shows various different fractals that are based on angle path. For example, this is the dragon curve and the Coke 2 curve. and the piano 2 curve. And they are space fillers. The dragon curve can be found by starting with 2 squares and shifting them like so, and then dividing again. And as you keep sliding and dividing, you get the dragon curve out of dominoes. In flakes, you basically start with a particular shape and then do recursions up to some level. So for example, here's the order 4 pentaflake. And here's a similar object with triangles or with squares. You can also do this with any right triangle. You just basically divide the triangle up by its hypotenuse, and then you do the larger triangle, and then the larger triangle again, and so on. And you get this series of divisions as you keep repeating the dropping of a hypotenuse. So I did a big demonstration on substitution tilings. For example, here's the square root of 2 tiling, or the almond chair tiling. I tried to put in every single known substitution system into this demonstration. I need to do updates because a few more have come out just in this past year. But there's about 50, I think, in this one. And as you increase the number of steps, they get more and more complicated. So one of the ones I need to add is this one by Vesa Timonon. This was just found last year. This particular 5-sided object, the numbers here are the plastic constant. X to the third equals x plus 1. The real value of x to the third equals x plus 1. So these numbers here are powers of that value. So you have the plastic constant raised to the power 0, raised to the power 2, raised to the power 4, raised to the power 5, and raised to the power 3. And if you combine 3 of these identical shapes, you get this shape on the outside, which is identical. So this is a shape that someone should have found a long time ago, but it was only found last year. And I tried to do this in my substitution tiling code, but I made a mistake somewhere. It's a little bit tricky to set these up, so I'll need to figure out exactly how that works. Several steps of the fractal substitution. Here's a similar object found by Carl Scherer, which has a similar structure to the Vesa discovery, but it has a simpler root instead of the plastic plastic constant. And here's another called the almond chair, found by Robert Ammon, who also found many different substitution systems. There's a program called IFS tile, which has hundreds of fractal irreptiles. And an irreptile is a shape where everything is identical to the outer shape, but there are different sizes possible. So here's various ways of taking a single shape and having 3 different copies of various sizes to reproduce the exact same shape. And you can see there's quite a variety of different objects that you can build with these fractal shapes. I know of, outside of the range of fractals, I know of these different shapes that are possible of order 3, where you have an object on the outside and you divide it into 3 similar copies of itself. I know 3 ways of doing it with triangles. There's 4 ways of doing it with rectangles, with trapezoids. I know of these 4 methods. This is the Vesa pentagon that I just showed, and I know of 4 ways of doing it with hexagons, as these objects shown down here. So the concept of a fractal is you basically apply a step over and over again. So here's the square root of 2 substitution tiling. All of these triangles are similar to each other, and when you make the substitution on the smaller triangle, you keep recursing, and you take that step and you apply it over and over again. You take the step and you apply it over and over again. You take the step and you apply it over and over again. You take the step and apply it over and over again. So here's a more complicated substitution tiling. This is the square root of chi tiling, which is one of the ones I found that I did an experiment in one demonstration where I tried to solve the question of how can you surround a point with similar triangles. And it wasn't too difficult to solve with a program. Basically, you figure out different ways that the sides could have relationships with each other as they surround that point, or 3 triangles, 4 triangles, 5 triangles, and so on. And then you just have the computer solve it for you. And that led to hundreds of different solutions that no one had ever seen before. And this is one of the results. This angle right in here, this is one way of surrounding that point there with similar triangles. And it led to the larger triangle on the outside, which is similar to every component triangle. So all the triangles in here are identical. And I believe that this is the most complicated single shape substitution system. Here's another that I discovered. You have a triangle that's based on 2. These sides are literally 2, 2, and 1. And if you add a line here, you get a similar triangle. This would be 1, 2, and 2 again. And as you do that substitution over again, you get this strange fractal down here. Here's the Walton chair, where you start with this substitution, and as you repeat it, you get this fractal shape. The almond chair leads to this sort of fractal. The similar phi chair, based on the golden ratio, leads to this fractal. The Penrose ROM, you have a skinny and a larger rhombus, and as you repeat it, you get this fractal. The kites and darts, you start with a dart on the outside, and as you repeat this substitution into darts and kites, you get this infinite shape. The Robinson triangles, similarly. And this is one that I found, the rho quad substitution. Rho is the plastic constant. X to the third equals x plus 1. And as you repeat that substitution over and over again, you get this wild-looking fractal. There's another triangle you can aim for, which is called the plastic fractal triangle. And the whole thing is the plastic fractal rectangle. These 2 shapes are also the fractal plastic triangle. And these numbers here, these are particular powers of a complex root of x to the third equals x plus 1. For example, if you find that complex root and raise it to the power of 7, you get this point. Raise it to the power of 5, you get this point. Raise it to the power of 4, you get this point, and so on. There's a whole bunch of different powers of the particular complex root that are found on the border of the object. And as you repeat this for the plastic constant, you get the relation that the plastic constant is equal to the reciprocal fourth power plus the reciprocal fifth power onto infinity. And you can actually demonstrate that by using plastic triangles of all these different sizes going to infinity. The psi quad substitution system is similar to that. And it's actually a self-defining fractal. So the super golden ratio is x to the third equals x squared plus 1. And if you find a complex root of that, which is right here, that's the complex root to the power 1, you get that the complex root to the power 2 plus 1 equals the complex root to the power 3. So literally, psi squared plus 1 equals psi to the third. If you take the fourth power and the negative of the second power, this dot here at the center is 0, you can connect these points of the powers of that complex root and get this particular substitution system, which is the psi quad system. And I'm amazed that I'm the one that found this. It was sort of the easiest to construct fractal I've ever come up with. In fact, it's self-defining. The points you need are literally given by the powers of the root of psi squared plus 1 equals psi to the third. And psi is the super golden ratio. You can also get this triangle with the chaos game, where you basically iterate these rules here. All the code for this will be in a community post posted sometime later today. But if you just basically randomly pick from the two options, you get these two fractal triangles, which combine to make a larger version of the same fractal triangle. We can also generate the wiggly path directly. I've got the code for that right here. It's not too difficult, and it's basically based on powers of the root. So basically, if you know the root of the fractal, often those powers will do a lot of work for you. And this is one fractal where just the simple powers do all the work. And as you take this fractal triangle or do a recursion with the psi quad substitution system, you get this fractal, which basically is the super golden triangle. And if you use multiple copies of it, you can get a fractal nautilus shape. You can also show that the infinite sum of reciprocal powers of the super golden ratio is a infinite recursion, as shown here. So I mentioned reptiles. Reptiles are simpler than irreptiles in that all the shapes are the same. So for example, the 1, 2 right triangle is rep 5. And there's various fractal reptiles that you can find. So the simple square is a rep 4 substitution. The wedge is rep 4. So this demonstration has many different fractals. The Gosper Island is rep 5. And we also have a demonstration on irreptiles, which has many more objects, in fact, 73 different irreptiles, many of which can be used directly in substitution systems. Not sure why I'm pausing there. Oh, here we go. So here's a fractal parameterization, and you can see where the point can be moved along the edge of a growing fractal, the Koch fractal. And for some reason, it's pausing on me. Let's see if I can get past that. Yes, there's a different fractal from that object. The octahedron fractal basically combines octahedra and tetrahedra to get a different fractal of various sorts. And here we take the fractal apart. And you can do the reverse of that with the fractal tetrahedron. The tetrahedron at the center. Another variation of this particular fractal. The Minger sponge, where you take the center out of the faces of a cube and then you repeat that. If you divide that in half, you get various fractal star objects. Let's see if I can go depth 3, like so. I believe the largest Menger cube that's actually been built is now order 6. Here's a similar thing with tetrahedra, but with spheres. And the Apollonian gasket also has fractal properties. So one thing you can do with fractions is make a infinite series of spheres, and all of these circle have radii, which are particular fractions based on the Ferri sequence. So if you do these, why isn't that working? So if you follow these instructions and build circles of these particular sizes, you'll get this series of circles which are all tangent to each other. One thing you can do with tetrahedra, there are 2 tetrahedra that I know of which can be used to make larger copies of themselves. You basically use 8 of them, and they meet together in a particular way to combine to make a object which is a copy of itself. Oops, and for some reason I am freezing here. Let's see if I can fix that. Uh-oh. Here we go. Thank you for not crashing. So here's the fractal ortho scheme for this particular tetrahedron. And I wondered how we could expand that. So I used barycentric coordinates to make a larger version of it. So here's a fractal tetrahedron where all the pieces are copies of themselves, or are copies of the outer object. There's another ortho scheme where you can do the same thing, but it's a little bit more boring. It's has a very repetitious nature to it, but still counts as a fractal. We can split cells in various ways to come up with other fractals. So here is the Afferman carpet. And another demonstration does the same thing, but has more options. So here's the Sierpinski carpet, Cantor dust, and the square fractal. Here's a version where we start with a cube at the bottom and we repeatedly divide as we move up, and we get a more and more complicated fractal. Here's another tree substitution where we experiment with branching, and there with various different replacement rules, you get different structures. Many of these are seen in biology. We can look at tree generation to generate fractals of various sorts. And we can look at the limits of tree branching, which is one thing that Stephen Wolfram covers in his book, A New Kind of Science, where he has a whole chapter devoted to the biology of different things that can happen as you vary the structure of how leaves grow and how branches happen. And he has pictures of a few hundred of these different behavior that can be seen within plants. Another view of the Sierpinski carpet. You can also look at the Sierpinski triangle, which is another sieve. And you can do this with superscript, the superscript function. We can vary Koch curves in various ways. And as we change the angle, well, that's a strange one, you get various different structures. This particular structure here can be seen within the Coca wave pattern, which I did a community post on yesterday. We can also subdivide polyhedra in various ways, as I showed earlier, to get these fractal structures. If we do right angles, we can get this sort of structure. Here's two different types of this, and here's all of them shown at the same time. Level 1, level 2, 3, 4, and 5. The Cantor set, where you start with an object, remove the middle third, and then the middle third of the remaining objects. This is a famous way of creating Cantor dust. And if you look at the ternary system, if you just look at the values of Cantor numbers, or the, excuse me, if you just look at the value of ternary numbers that lack a 1, you'll get a Cantor dust of integers. You can also do ternary decimals, and the same thing happens. You get Cantor dust when you look at the ternary values that don't have a 1 in them. And in fact, this is a representation of the numbers you'll get in ternary decimals. And as you use that, you can build functions out of it. For example, I think the next one is the Minkowski question mark function uses properties of the Cantor function in order to build the strange curve. I should have had that before that one. So this is another Cantor function using different iterations of it. And this idea of repeating an operation over and over again can be used to make very strange functions which don't have properties of differentiability, which means they're not smooth anywhere. For example, this particular curve here, found by Riemann, is connected everywhere, but it's not smooth anywhere because it has a very strange definition based on recursion. So fractals aren't new. They've been in use for thousands of years, really. The original Archimedes demonstration of the area of a circle was based on infinite recursion by splitting up the triangles used to define the area of a approximation for a circle. Here's a function which is very similar to the way marks on a ruler appear, but instead of just force, halves, force, eighths, and so on, you use more complicated values. And the particular pattern that you get is known as the Dirichlet function, or the Tomei function, or Riemann, or popcorn, or ruler function. The Dodaki curve is a sum of different zigzag functions and has this weird behavior, and it's gotten the name of the Blancmange function. Here's another function which is connected but not differentiable anywhere by Bolzano. And the question mark function I showed earlier based on this particular setup. And we can vary it in various ways. If we look at partitions, they also have a fractal nature, as shown by George Beck in this demonstration. A partition being ways of splitting up a number into integer parts. For example, the partitions of 4 are 4, 3 plus 1, 2 plus 2 plus 1 plus 1, and the sum of ones. And as you look at these partitions as numbers get larger, they have more and more of a fractal nature. We can look at generalized Cantor sets as shown here, middle sevenths, for example. So these are different ways of playing with different number bases and the behavior of the numbers within those. I'm not sure. Yeah, this is just an image here. So here's the pinwheel tiling. Some of these slides are from my talk on the hat tiling. Here's the an example of a fractal tiling called isopenta, and also the, oops, I guess it didn't want me playing with that. Let's see if I can bring that back. This is the Penrose tiling in a strange way, because this is a 3D object where all of the rhombuses are identical to each other. This is known as the Wieringa roof. And I think I can go one more step. So this is a fractal pattern in 3D where we use all identical polygons, but they're at strange angles to each other. We can add a bit of transparency here. And all the code for this will be in the community talk later. I'm not sure if there's other substitution systems that have 3D equivalents. So I consider that an unsolved question. If you do know of any 3D expansions of 2D substitution systems, I'd like to know about them, especially if they start with two different shapes, but there's a 3D transformation to make them identical. I'd like to hear about that. So I think this is just an image here. So this is another one of the reptiles. And I showed various other reptiles. For example, the Robinson tiling. This is an example of a aperiodic set instead of periodic. The ones I showed earlier, there was a certain periodicity to them. For example, a chessboard is just a periodic arrangement of squares, but we can also get stranger behavior that can be forced with particular sets of tilings. And that was finally done. A single shape that does that was found a few years ago. All of these objects within these values here, these all tile the plane in a aperiodic way. And up here it shows how those tilings look as they're expanded. And there is a substitution system using them. These are basically the rules for it. Just over 2 years ago. Here's a larger patch of the hat. And as you color the different angles that the hats can be at, you get these strange patterns within them. For example, you get this orange-pink line here and a yellow line here. So this was a big study for a while. You can also look at how the items are arranged if you color them, and you get this strange two coloring, which has things like the Sierpinski triangles within them, but it's more complicated. You get this strange fractal shaping as you take large patches and you color the tiles in a particular way. So here's a way of turning the hat into turtles instead. And we've got several functions within the function repository where we have different ways of generating the hat tiling with, for example, the triality tree, which we found earlier. So away from the hat, there's even more fractals. For example, we can vary up how different flips are done, and we basically reduce everything, we replicate it, and we rebuild again to come up with different fractals. Tangent circles leads to many different fractals. For example, this item here with recursions of tangency. Jamie Randall Monderground also came up with a whole series of, I think, 30 different fractal demonstrations. I've got 99 slides here, but I could have done 1,000 different slides because there's just so much material I've got on fractals. So I sort of wanted to limit it to the better stuff. Let me see here. I'm looking to see what's been posted here. So let's see. Here's a exercise that he did with rectangles. For example, the P pentomino, we can get a whole bunch of different copies of the P pentomino. I'm still looking for more 3D fractals. For 3D substitution systems, not very much is known. Stacks of cubes, a homage to Escher. Here are some of the different L system plots that are possible. The Gosper curve over here. And we have a resource function called Schmidt arrangements, which does many different things with fractal circles. So here's 3 different examples of those. Here's a order -3 Schmidt arrangement. The curlicue fractal is just basically taking a particular value and iterating it to come up with an angle, and then just doing that over and over again. And different combinations of well-known constants will come up with different fractal patterns, which are not immediately obvious for the constant that's being done. For example, if you multiply pi times the log of 2, you get this strange fractal. If you change it to log times the golden ratio, you get that. And with log times the k constant, you get something strange. And it's interesting how each of these seems to have a different character to it. Seems to be taking a while on the plus here. Oh, that was times. Let's see what plus is. So you can see that there's different strange behaviors based on how you pick your constants. And I don't know why. So one question is, what particular constant has the highest temperature? For example, log 2 plus log 3 has a very high temperature. I run a Facebook group on tilings, and there's various artists who have contributed quite a few things to the tiling group, and it's basically Facebook tiling. G. Byom Kim has many fractals. These are just fractals he's come up with in the past month. These different shapes. For example, this is a golden ratio based sequence here. Here's another one based on the golden ratio. He does both 2D and 3D substitutions. So that is Ji Byom Kim, who I believe does more different types of fractal substitution art than anyone else at the moment. I've also done various different talks relating to fractals, including the Turing machine talk, the 19th of these. Here are different fractals based on 1D and 2D Turing machines. Another talk I gave that dealt a lot with fractals was my talk on space filling curves in both 2D and 3D. And my talk on the hat had many different fractals within it. So I have a few questions that I I don't know the answers to. So I showed the 2D Pembus ROMs will become a 3D Wieringa roof. What other dissimilar piece substitution have a 3D equivalent? A open question, what substitution systems haven't been found yet? I also mentioned that I found a whole family of about 50 different substitution systems by answering the question of how do you surround a 2D point with similar triangles? That was pretty simple to solve, and it led to a whole bunch of different objects. But one thing I haven't been able to solve is how do you surround a 3D point with similar shapes? I haven't figured out a good way how to solve that. I don't think it's too hard of a problem, but I haven't been able to solve it. So if anybody can solve that problem of how can you surround a 3D point with similar shapes, that might lead to a whole bunch of different things. And I should probably try to expand that to how can you surround a 3D point with two similar shapes. Let's see, gecko feet were figured out less than 20 years ago. They have a fractal application of van der Waals forces, and that's why geckos can stick to things because they have fractal setae on their toes. And I'm wondering what other applications there might be for fractals that haven't been discovered yet. Here's a 3D fractal. If you take the whole object and take 8 copies of it, you'll get each of these splits for this is equivalent to the larger object. And I'm wondering what other 3D fractals are this complicated. Excuse me. So that's what I had so far, and I'll be glad to answer any questions. Let's see. So if nobody has any questions, I think we can wrap it there. Many thanks for attending, everyone, and we'll have this posted sometime soon.